All right, to finish out chapter 12, we're going to very, very briefly talk about solids. We're mostly going to focus on the idea of something called allotropes. These are different molecular structures for an individual element. So not compounds, just one element. Okay, so I guess I'll write all that out. So different molecular structures. So basically how the individual atoms are connected together for the same element. We'll start with a really easy one and then talk about the stereotypical one that everybody talks about. Okay, so for example, oxygen. Okay, oxygen never exists as just an oxygen atom floating around by itself. It just doesn't. Okay, there's basically two options. It can either be O2, which is the predominant one, the oxygen that you're breathing in right now to keep you alive, or O3, which is ozone. Okay. Both of them are entirely made of oxygen. Both of them are reasonably stable. This one's super stable. But ozone does exist. It's not like a super unheard of molecule. Has a negative charge on that, a positive charge on that. Not the most stable thing in the world, but you know, this exists in the upper atmosphere, helps block out ultraviolet rays so that you don't get as much sun, not as high of a risk of sun cancer as you might have otherwise. Oxygen is, you know, literally what makes the world go round at this point. It's the reason there's life on this planet. It's what most chemical reactions are based around. Okay, but the idea is these are two different structures for the exact same element. Okay, the stereotypical example that everybody talks about is carbon. So I figure I should do this justice and make sure that I talk about carbon. Carbon has several different forms that it can exist in. The first, the most stable, is diamond. So, if you've ever seen a diamond, it's literally this really pretty, clear crystal. Okay, true diamonds are only made out of carbon. They all are tetrahedrals. And they're very, very stable. So in other words, what you have is a carbon, and it's got this kind of tetrahedral geometry, and then there's carbons that are all tetrahedrals at the end of all of those, and it just goes on forever and builds this huge crystal. Okay, but tetrahedral is the most stable option for a carbon, so it makes sense that this would be a very, very stable molecule. Okay. Another option is graphite. I know I'm writing this with pen and I don't have a pencil anywhere around, but pencil lead. Okay. This is also only carbon. Okay. These are all in the trigonal planar geometry. So the Vesper theory stuff from last semester, trigonal planar, it's supposed to be an L, sorry. And what happens is trigonal planar is some of these are going to be single bonds and some are going to be double bonds. Okay, but everything is flat. Okay, and what happens is it forms these huge sheets, and then the sheets are barely able to interact with each other, and they lay on top of each other. And that's actually how pencil lead works. Is essentially what you end up with is it forms these thin sheets. So this is the graphite. And as you push on the paper, which has like a slight bit of texture to it, the sheets are easily separate. They're stable in one plane, but they're not connected to each other very nicely. So what happens is as you rub a piece of pencil across the paper, these layers are just ripping off and being left on the paper and squished on there because of the texture of the paper. Okay. Not a huge deal, but these are the two most likely options. If you encounter like coal, it's pretty similar to the structure. It has a lot of impurities in it, but it's essentially this. Diamond, primarily, if it's a really high quality, high carat diamond, it is primarily just this. You can also buy black diamonds, which are actually super rare, because it's an even distribution of this stuff mixed in the middle of this. Okay. But these are not the only two options. Another option is something called Buckminster Fullerene. Probably not going to do a great job of describing this. Buckminster Fullerene. Okay, so any of you have ever been to Disney World, Disneyland? I can't remember which one it is. They have Epcot Center. It's like this huge sphere thing. Or if you've ever seen a soccer ball, like the one with the hexagons and pentagons on it. That's essentially what Buckminster Fullerene is. Okay, it has a specific, so like with diamonds, you know, this could go on forever. For graphite, it can go on forever. This is actually a really specific molecule. It's carbon 60. Okay, and it's literally in a soccer ball shape. So what I mean is like pentagons surrounded by hexagons, and everywhere, and it'll form this, you know, it'll form a ball. And everywhere you have an intersection, you would have a carbon. And they're all sp2 carbons, so they're all trigonal planar, but they're not planar because they curve and form a sphere. Okay, so every carbon's going to have one double bond and two single bonds, and somehow, I don't know the exact pattern, but it all lays out so that you end up with this three-dimensional sphere. So if you've ever seen a soccer ball, it's literally exactly the shape of Buckminster Fullerene. Okay, there is also another option called nanotubes, and they're basically a Buckminster Fullerene, but it's like stretched out so that it's like round at the ends and it just forms this long hollow tube. It's still trigonal planar carbons. When I was in high school and in college, apparently I can't write an L, planar. When I was in college, these things were being discovered and mass produced for the first time, and people were like, "Oh my God, they have these electrical properties, and they're gonna revolutionize the world." Yeah, they're really not that important. They haven't. They look cool and they're interesting to manufacture, but they aren't really as functional as people thought they were going to be. But the idea is this is still only carbons. Okay, so the idea though is that basically, you know, if you have carbon and it's just carbon, it's probably going to exist in one of these four options. I will say that these two are the most likely. These two are kind of man-made ones that can exist. I actually did a lab in my senior year of college where we actually made Buckminster Fullerene. It's not that weird to make. You basically take graphite and just electrocute it a lot under really, really low pressures, and these things just kind of form and you have to filter them out and find them. It forms like this really pretty purple liquid, but it's kind of cool stuff. But the idea is that naturally occurring elements form these natural forms, or form these natural structures, and they have different properties and they function differently. Some molecules only have like one specific option, like sulfur always exists as S8. Okay, on balancing equations, we usually just write it as an S, but essentially what you end up with is this zigzag pattern. I don't know how to draw this. 1, 2, 3, 4, 5, 6, 7, 8. I don't know how to make that connect. Whatever. It's like a zigzag kind of. It forms like this weird crown shape. But this is it only has one option. So basically, not an allotrope. Or like, you know, we talked about oxygen can be O2, but things like chlorine or bromine or fluorine or iodine only exist as F2 or Cl2 or Br2, so on. They only have one option. So this isn't a huge deal, and we're not going to make a big deal out of it, but I just wanted you to have at least heard of it. All right, thanks.